Martine talked about dihydrosphingosine 1-phosphate. Obviously, I've been giving lipid talks in the last couple of weeks. And for this talk, we're not even going to talk about the lipids.
Oh, okay.
Is that much easier?
Well,
Because I want to talk about a therapy.
Photoimmune nanotherapy is a
I
great
want to talk
idea.
about a therapy.
Yeah.
I want to talk about a therapy that uses nanotechnology that upregulates the immune system and makes a theranostic, which is the word that the NIH is using right now. Is a therapy, it's an imaging agent, and a diagnostic all in one.
Great.
And I'm going to
Even
show you
better.
how to commercialize it and how to try to get it from the bench to the bedside. I'm a faculty entrepreneur, so basically I do work for Penn State College of Medicine. However, let's see, next one. That's not the right way. I also have co-founded a company, and this is my slide to remind to tell everybody in conflict of interest that I'm Chief Medical Officer of Keystone Nano, and I formed this company with Jim Adair, who's a National Science Foundation head of the Particulate Materials Center, and he was a nano geek. And he came to me and said, I can make deuterium, I can make gold, I can make cadmium, selenite, and zinc. And I go, and what do you want to do with it? He goes, I want to cure cancer with it. I said, I'm not an IBM computer. I'm not cadmium, I'm not selenite, I'm not zinc. Can't you guys do something simple? Can't you do something out of a biodegradable, biobenign compound? What about calcium phosphate? So I'm going to show you how calcium phosphate, and there it is right there, can be made on the nanoscale and be used to encapsulate and protect. And what I'm not going to talk about is small molecules, say like doxorubicin, or small interfering RNAs for molecular-based therapeutics, but I'm going to try to show that we can actually harness the power of light for theranostics, truly to use light to kill cancer cells. So with that, just for a background, we now call these materials nanojackets. Why? Because Nature wrote a nice article about us, and they used the word, and I said, all right, that's great, because they're dressed to kill. And that is one 20 nanometer size nanoparticle of calcium phosphate. And what makes this particle different from all other nanoparticles is it's amorphous. It's, for lack of a better word, porous. We can put the active ingredient inside the nanotechnology. A lot of nanotechnologies are solid, and you put the active on the outside, so it could be degraded, metabolized. It's not going to work. We actually put the active inside the nanomatrix. And here we have an example of 5 different fluoroprobes inside the nanomatrix, inside the calcium phosphate nanoparticles. And we've published now in ACS Nano, Nano Letters, over the last year and a half that these materials are biobenign, biodegradable, and we'll talk a little about that right now. So what also makes these particles unique is they're biosmart bombs. We've engineered them to be stable at pH 7.4. In fact, those fluoroprobes you saw before are now going on 2.5 years. And if you've ever taken a fluoroprobe, put it on the desk, within a couple of days, let alone a couple of hours, they photobleach, they photodegrade, they no longer fluoresce. Our materials can stay inside these nanoparticles for 2 years and counting and still fluoresce. So we truly get that protection. But what's nice is they're stable at 7.4, but they're designed to dissociate, to dissolve at pHs below 5.5. So we take advantage of the cell's ability to pinocytose these materials, which are 20 nanometers in size, non-aggregating. They actually end up into the cell through pinocytosis, and as they end in the early endosome, as the pH falls, and we've now published this in 3 different publications, the calcium phosphate matrix dissolves, out comes your active. The phosphate now acts like a buffer. The endosome doesn't like to be buffered. It explodes. Out comes your material into the cytosol. And if it's a small molecule or siRNA, that's exactly where you want it. So we now have a trigger that we have designed inherently in the calcium phosphate nanoparticle. Here's a TEM of the calcium phosphate nanoparticles. Notice they're non-aggregating. They're not agglomerating. We can actually make a solution of 10 to the 15th particles per cc. That's 1,000,000 billion particles. Surprisingly, that's not a lot of calcium. When we actually deliver a bolus systemically through a tail vein, in, let's say in a rodent model, we're actually giving less than 10 to the negative 7th molar calcium, which is 3 orders of magnitude below systemic load. A lot of particles, not a lot of calcium, but a lot of drug and or active ingredient. Notice these particles are 20 nanometers, plus or minus, very tight distribution, and they don't aggregate because we can actually passively passivate the outside of these surfaces with pegylations, etc., so they act like Teflon and they don't aggregate among themselves. They don't become macro and become lunch for a macrophage. So those particles we just saw before were actually loaded with indocyanin green. It's a near-infrared photoprobe. It's FDA approved, and it's used for imaging of the peripheral posterior segments of the eye, and it's also used for other medical indications. What we've done is inside each of those particles, we've put indocyanin green. What are the limitations of indocyanin green, and what do I want it to do? Well, the problem is it's relatively unstable, it dimerizes, it quenches, it basically binds to proteins, and the plasma half-life is on the order of minutes. When we have our materials in systemic circulation, we get half-lives of 18 hours. Huge difference. The benefits of the encapsulation is the caging within the calcium phosphate nanoparticle prevents agglomeration. Basically, we get photostability by putting pegylations on the outside of the calcium phosphate nanoparticle, and we can actually move these indocyanin green molecules into the tumor, as you're going to see momentarily, to allow imaging of tumors, and you'll see we can go as far as 6 centimeters. You start thinking mammography at this point. So I'll just give you a little of the biophysics beforehand. We had to make these materials stable in physiological solutions. A lot of nanoparticles are great, but as soon as you put them in physiological buffer saline, let alone the body, they self-aggregate, they agglomerate. Our materials are delivered in PBS or equivalent and do not agglomerate. Here's an example of up to 288 hours of these materials in PBS, and you can see the size doesn't change. And this has all been published in ACS Nano, so we'll go quickly through this first 5 or 6 slides. Notice we get an increase of the fluorescence when we encapsulate the indocyanin green. And we actually use fluorescent correlation spectroscopy with some of our partners, Peter Butler, Peter Eklund, and we get quantum efficiencies of 2 to 5-fold when we encapsulate, because we don't get the photo degradation and or the photo aggregation. When we actually measure, we take a laser and we actually excite these calcium phosphate nanoparticles, and we're going to use this in the photodynamic therapy coming along. We see that when we encapsulate these indocyanin green photoprobes within the calcium phosphate matrix, that's the blue, compared to free indocyanin green, which is just indocyanin green without being encapsulated, you can see at both wavelengths, power intensities, you get increased fluorescent lifetime of the indocyanin green. You protect it within the calcium phosphate nanoparticle, and for any amount of energy going in, you get multiple bangs for the buck of energy coming out. The other thing we've noticed, that if you took indocyanin green and you actually measure the fluorescence in different medium, let it be H2O, DMEM, PBS, DMSO, the wavelength shift is very, very unstable. This is the free indocyanin green. When we put the indocyanin green in the calcium phosphate nanoparticles, the curves superimpose, again showing protection of the indocyanin green within the calcium phosphate matrix. So what can you do with this? Everybody talks about enhanced permeability and retention, the ability of a tumor to grow quickly, want to form a vasculature. They form a vasculature very quickly, but not that well, and materials come in, but they don't come out. This is an example of using photo imaging with the indocyanin green to actually look at enhanced permeability retention. All our animals, we got 4 animals, they follow them over time, 15 minutes, 3 hours, 24 hours. He moved over here. We have another picture where he didn't move. 48 hours out to 96 hours. Animal 1 just got ghost calcium phosphate nanoparticles, just a calcium phosphate nanoparticle, no fluoroprobe. Animal 2 gets the free indocyanin green, just the indocyanin green, not encapsulated. Animals 3 and 4 get the indocyanin green within the calcium phosphate matrix. The 4th animal, that matrix, that calcium phosphate nanoparticle, is highly pegylated, which will increase the T1 half of the material. Let's go down to the 96 hour. These 2 little headlights over here, that's the tumor.